Hi guys. In this video, I want to talk to you about the relationship between voltage, current, resistance, and try to develop your intuition for it. I want to do that through using this setup right here that I've been set up using the PhET simulator. What I have right now is a one battery hooked up to a light bulb, and then it's just the one battery on loop. If you visualize the current, this is the flow of charges, and I can use an ammeter. This isn't an actual ammeter, it's kind of just cheating by just kind of seeing through the wires. And you can see that the current right now is that. If I was to add another battery here, what do you think would happen? Before it was 0.9 and now it is 1.8, and you can see the brightness of the bulb the lines went farther, meaning it's brighter. What do you think is going to happen if I add this third one? It was 1.8 and now it is 2.7, and it's even brighter. The lines go even further. What do you think is going to happen when I add this fourth battery? Let's find out. I'm going to attach the top end here and the bottom end up there. Huh. The current went down. That's kind of weird. Maybe I just need to add another battery. Maybe something's weird with that one. 0.9. That's weird. I think I just need one more battery. That'll really do the trick. And now the bulb doesn't light at all. So take a minute, think, why does that happen? You might have noticed, well actually, let's just think about this for a second. So if I look inside, the charges aren't flowing. So why aren't they flowing? A lot of people want to associate batteries with energy, but this idea of voltage is a little bit more useful, and we got to develop a little bit. So I want to just check, hey, my batteries are working. Yeah, it's a 27 volt difference between them. So those batteries are working, and these batteries are also working. It's a 27 volt difference. But that's the difference between these 2 points. Notice that the low potential end is connected to the low potential end. The low voltage end is connected. And so what you have here is the high voltage end is connected. It's almost like this is a peak and this is a peak, and those peaks are connected. So you're not going to get any charge flow across the light bulb because there's no difference in height, essentially. I also think of voltage a little bit more intuitively as because that change in height sort of corresponds to the strength of the electric field in that little distance right here. When there is no height difference, there's no electric field difference, or there's no electric field pointing between those 2 points. So there's no push. Right now, the battery is pushing sort of this way, and these sets of batteries are pushing this way, and those pushes sort of cancel out. Those heights are canceling out. So what do I need to do? If I flip this around and basically get them pointed in the same direction, the easiest way, I guess, is to sort of flip it. And sort of connect this high voltage end to the low voltage end here so that they sort of add up. Now those voltages are going the same way, and you'll see the voltage difference there is, well, the size of it is about 54 volts. So that kind of corresponds to the difference in voltage there. So how do you think about this intuitively? I have another analogy. Let's see. So this is my little demo. Um, it's 2 syringe tubes connected by a thin tube. Put some Gatorade in there so you can see it. And right now, you can see if I lift one, the water goes to the other, and vice versa. If I put them really close to each other, you can see that the flow sort of takes some time to equalize out. It's kind of slow when it's just like a small change in height. But if it's like a big change in height, whoa, that's when it flows a lot. So this difference in height, what do you think it corresponds to compared to our circuit? Pause. That difference in height is like the voltage difference between 2 points. And the flow of charges is like the flow of this Gatorade right here. And what do you think, besides the difference in height, is affecting that flow of charges? The wire. The length of the wire and the area of the wire, that also affects the flow of charges. If it's like a longer wire, that's going to reduce the number of water molecules per second that are passing any one point. And if the area was smaller, if it was thinner, that would also reduce. And that kind of tracks with resistance directly. To sort of sum up, the way that I think about voltage, voltage is like a push, and it's that difference in push between 2 points that causes charges to flow. And somehow there's like a chemical reaction that's maintaining that voltage difference inside the battery, so that doesn't just go. It's not like a spark. A spark is a momentary voltage difference, but this is like a maintained voltage difference. The greater the push, the greater the flow in charges, kind of like that greater difference in height. And it's really important to associate resistance with like a static thing. That's like a property of materials. There's things that affect it, but it belongs to the materials. Whereas the voltage difference, I can apply a greater voltage difference, and because of that greater voltage difference, you're going to get more or less charge flow. And then just with this little analogy, this is really what I have in my head. It's like that difference in height corresponds to that difference in the greater the difference, the greater the flow, and then that the tube elements affect that flow as well. And to put this all together, it's kind of like a visual representation of Ohm's law. This, I did not come up with this. This is from Ohmify, but this is the voltage, this is the resistance, and this is the current. The voltage is pushing the current through, the charges through, and the resistance sort of affects that flow through the properties of the circuit elements. Hope that was helpful. Take care.